Welcome back. This is going to be a funky kind of lecture because there is so much material here that I'm going to just sort of skim briefly over many of the astronomical concepts. There are 3 different PowerPoints that deal with astronomy and astronomy topics. They're listed in your modules as chapters 21, 22, and 23. I go over a lot of these things in my astronomy class in a lot more detail than what I'm going to be doing here, because I'm mostly going to talk about astronomy as it pertains to Earth and Earth science, and I'll just briefly touch on other things. So if you want to know more about the stuff, you can sign up for my astronomy class, my solar system astronomy class, which is Astro 101. There are 2 different astronomy classes, and I won't be touching on things that deal with 102, which is stellar and galactic astronomy, which gets way, way out there. I invite you to look over all of the PowerPoints, and I also just want to reiterate, I'm going to try to hit all of the key points that might show up on your quiz, but all of the information that you might need for your quiz answers is in one of those PowerPoints. So you might need to skim around in them. But remember, you can do your quizzes open notes. So one of the things I would suggest you do is open up the quiz and open up the PowerPoints and read along. And as you're reading along, you can answer your questions. You also might have your quiz open while you're watching this video, because I might hit on some of the questions directly. I'm going to try to cover the things that are most important for us. So let's see, without any further ado, let me go to our first sharing of the PowerPoint screen here. And this is the one, I believe. No, this is not the one I want to do. I want to stop sharing that one. Share the screen. I want to share chapter 21. And why is that not showing up for us here? I think this is what we should be seeing here. So I will go up to the beginning here. And you know what? I'm actually a little bit concerned that you're not seeing what I'm seeing, because Zoom has done that before. So I'm going to pause this video and I'm going to start again after I can verify that this is doing what I need it to do. Okay, I am back, and it seems like it is sharing the right thing. It's not showing you what I'm seeing, but we will make do with what we have. And here we go. So let me start the slideshow here. This is an image from the Bayeux Tapestry, and one of the things you might notice here, we have a comet overhead. Notice all the people on the left here who are pointing up the comet. Look at King Harold sitting on the throne here. He's looking rather downcast. Comets are usually portents of doom in the past. And what this is telling Harold is that he's not likely to stay on the throne for very much longer. And of course, very shortly thereafter, William the Conqueror comes and shoots an arrow through his eye and becomes king, and Harold dies. But the reason why this is significant is when Edmund Halley, of Halley's Comet fame, was figuring out that the same comet can come back again and again and again, one of the pieces of evidence was this tapestry here, because he could do the math and he could tell, okay, every 75 years we have people reporting that this comet seems to be overhead in the same part of the sky. Stella up here, it means star, so we have an immigrant or itinerant kind of star. That's what a comet is. It doesn't last for very long. And it worked out mathematically. He was finding every 75 to 76 years, including 1066 when this was here, that the same comet shows up every now and then. There are lots of weird things out in space. We have this is a sort of a graveyard of a star. This is what happens when a star explodes. This is the Crab Nebula. When we are looking at our own planet, however, we are in Earth science, so I'm going to try to focus just on Earth science. You may know that people out there sometimes like to think that the Earth is flat. Well, we've known that the Earth is not flat, at least the people who know about such things, which should be most people, by the way, have known that the Earth is not flat for thousands of years. There's this idea that people still in Christopher Columbus's day in 1492 were worried that he was going to fall off the edge. No one was worried that they were going to fall off the edge, because for thousands of years by that point, people had already known as well. And one of the ways they do that is we have this guy named Eratosthenes. And Eratosthenes figured out that in certain parts of the world, this place called SCIN here, on the longest day of the year, the sun is directly overhead and nothing casts a shadow. Well, he read that in a book, but he's up here in Alexandria, and on the longest day of the year, when the sunlight hits a column or tries to go down a well, it casts a shadow. Well, the only way that can happen on the same day is if the Earth is not flat, but if the Earth is curved. If the Earth were flat, you would still have no shadows on the things anywhere in the planet. So what he did was he hired a guy to walk out the distance. And that distance is about 1/7, you sort of see we have the whole circle there, 1/7 of, or 1/50th of the whole circle at 7 degrees. A whole circle is 360 degrees. So you multiply 7 by a little over 50 and you get the whole circle. So he took that distance, multiplied it by a little over 50, and figured out just how big our planet is. This place where the sun shines on the longest day of the year, called the solstice, and doesn't cast any shadows, that is called SCIN. That's also on a line around our planet, which is called the tropical line. We have one in the northern hemisphere and one in the southern hemisphere. And that is the northernmost point and the southernmost point, the Tropic of Cancer and the Tropic of Capricorn, where the sun is directly overhead. We are north of that, so the sun is never directly overhead for us here in Indiana. It's always at an angle, and we always have to look towards the south. But this is one of the sort of short and easy ways in which we can figure out that the world is a sphere, that it is curved, that it is not in fact flat. The ancients were pretty clever. They invented some devices. They constructed some monumental architecture like we have here at Stonehenge, the bottom picture here, moon circles in Scotland that follow the things in the sky. The moon circles actually would cover things over an 18-year period. Stonehenge is set up so that the sun comes up and goes down between the stones on certain key days, like the longest day of the year and the shortest day of the year. Also in the equinox days, which are the days halfway between those two, and cast no shadows, so that you would know what was happening. These help mark the seasons and help mark the changes in the sky. People began to record these different events when we developed writing. This is cuneiform writing. There are different languages. Cuneiform is a kind of script, but there are different languages that use it. Just like French and German and Italian and Spanish and other languages in Europe basically use the same alphabet that we use. They might have the occasional different letter here and there, or umlauts or other kinds of markings, but they're basically the same alphabet. Cuneiform was the alphabet for many different languages. So we have several languages that grew up in the ancient Middle East, and that has led us to understand that people were tracking the stars and the planets way back then, because many things that we've recovered from that time are astronomical documents. People could see up in the sky, as you can see if you're watching this in the fall of 2020, you could see Jupiter and Saturn and Mars in the sky at night and Venus in the early morning. And one of the things that the ancients noticed is that these 5 planets, including Mercury, that you can also see sometimes with the naked eye, move through the sky. They're not always in the same place at the same time, just in the same way that the moon and the sun move. So they called those planets. We no longer call the sun and the moon planets, but they are wanderers, and that's where that word comes from. If we look at Mars on any given night, for example, say here we're seeing Mars. Mars does look a little bit red. And we come out a couple of days later, we're going to notice it's changed. Notice we've got these two, we might say marker stars here. It's between these two. It's still between these two, but now it's moved a little to the left. And now it's outside being between those two, and it's over here. As time progresses, you can't really watch it move in the night. It doesn't move that quickly, but you can watch it move over the course of successive nights. And that's what all of the planets do, the sun and the moon also. So people began to think, well, everything's going around us. Sort of makes sense. I'm not going to fault any of the ancients for thinking that, in large part because that's the first thing you would think. You would think that I'm standing here on Earth and watching everything go around. Thales of Miletus is one of the first ones who figured out that we can understand where things are. Thales was credited for being the first person to predict an eclipse. You can understand that an eclipse is coming by knowing the pattern of the sun. You've figured out the pattern of the sun. The sun comes up every day, goes down every night. It takes about 24 hours. So that's a pattern. It's predictable. The moon follows a pattern. We can watch its 8 phases. It goes from new phase to first quarter to full to last quarter and back to new with a couple of other phases in between there, like clockwork. Every now and then the moon gets in front of the sun. You can predict that pattern too. It's not just one god getting mad at another god and turning off the sun for 3 minutes. Pythagoras, you probably know that name from the Pythagorean theorem. He said you can put numbers to all of this. You can't just understand the patterns, but you can actually understand how to calculate them out. Plato, who came a little bit later, said that pretty much everything in the universe can be understood in this way. And he actually thought that numbers and those ideas were more real than the stuff that we can touch and feel. Aristotle then came along later, who was one of Plato's students, and formed this big, what we might call cosmological structure, with the Earth in the middle and everything going around the Earth. And there were 55 different spheres. So it's sort of like those Russian nesting dolls, where you've got one inside of another, inside of another, inside of another. And the Earth is the one in the middle, and all the other things are going around in different spheres. Well, why are there 55 of them? That's largely because you need 2 or 3 different spheres to explain how the planets move. The planets are sort of locked between the spheres. And it was a really complicated way of thinking about it. But one of the reasons they needed those extra spheres is sometimes we have retrograde motion. That means as we're watching Mars go through the sky, sometimes it seems to stop, go backwards, and go forwards again. Well, why does that happen? Well, if we're going around the sun here, say here we are on Earth, and this let this outer planet here be Mars. When we're at point A and Mars is at point A, when we're both at time where they're the same time, when we're looking at Mars from where we are, it would look like this at the back of the stars. When we get to B, we've moved here, and Mars has moved here. We see it has moved across the sky. But by the time we get to C, it looks like Mars has moved backwards. Now, Mars hasn't moved backwards. We've just moved forwards faster. Then by the time we get to D, it looks like it's moved even further backwards. But by the time we've rounded the corner, it's up to E. And now it's going forwards again. That's the retrograde motion. It's not actually going backwards. It's because we are going faster. The closer you are to the sun, the faster you go. The further out you are from the sun, Mars is further out, Jupiter's further out, Saturn's further out, they seem to go backwards for a time. It's because we're lapping them. You can sort of think about that like in a NASCAR race or an IndyCar race. I mentioned this, I think, in our lab. where if you're looking at a dash cam and it looks like the cars on either side of the dash cam are going backwards, they're not actually going backwards. It's just the car with the camera you're watching is going faster forwards. So that doesn't quite work if you are having the Earth in the center. So we had this guy named Ptolemy. Ptolemy came up with the idea of an epicycle. And an epicycle is a sort of a loop-de-loop. So as the planets were supposed to be going around the Earth, they were also doing these loop-de-loops called epicycles. And that would explain why they sometimes go backwards. But it didn't really predict exactly where they were going to be. So they had to move the Earth off center a little bit. And then they had to move the center of the loop-de-loop off a little bit. It's because they wanted everything to be in perfect circles, but nothing was actually going in perfect circles. But this explained okay. I'd say I'd give it an A- in terms of accuracy of explaining where the planets are. So this worked for about 1,500 years. We call this a geocentric model, Ptolemaic model, because Ptolemy came up with it. And everything seemed to be going around the Earth. Well, over time, it's sort of like a clock that's running slow. With each successive generation, it's less and less and less predictable, or less and less and less accurate in its predictions. So instead of being an A-, it'll go to a B+, and then a B, and then a B-, and then a C. And then all of a sudden, you'll realize, oh, these are months out of date. So along came a guy named Copernicus. And Copernicus was a minister, he was a priest, he was someone who studied medicine and law as well as astronomy, spent 40 years or so looking at the sky and trying to figure out, can we revise? First of all, he wanted to revise Ptolemy's system, but then he also proposed that if we were to put the sun in the center rather than the Earth in the center, we might be able to get rid of some of these loop-de-loops. Well, he wrote a book called On the Revolutions in the Heavens, and of course the revolutions was revolving around the sun, but also a revolution in thinking. He put this book out in 1543. He also passed away in 1543. In fact, legend has it that he got the published book the day he died. But it actually didn't predict where things were going to be in the sky much better than what he was using with the Ptolemaic system. So he said there are a couple of ways you could verify whether or not things were going around the Earth or the sun. One of the ways would be if Venus had phases. See, if Venus is going around the sun, notice sometimes we're going to be seeing the backside of Venus, or we're only going to see little slivers, crescents. Sometimes we'll see half of Venus, and sometimes we'll see almost all of Venus. Well, with the naked eye, you can't tell that. And they didn't have telescopes in Copernicus's time. Telescopes didn't come along for another 50 years or so. In the meanwhile, we had this guy named Tycho Brahe. And Tycho was sort of my favorite guy in terms of medieval astronomy. He was a really great observer. He died in 1601, and again, he just missed the telescope by this much. It came along in 1608 and 1609. But he was probably the best observational astronomer, the best person to ever go out and look at where the planets are. And he did it for 30 years, painstakingly getting better and better and better measurements. He measured a star that exploded, like the supernova Crab Nebula that I showed you before. He measured comets and could tell that comets were actually a long way away. Before then, people thought that comets were like clouds in the sky. But he figured out that, in fact, they are quite far away. And one of the ways in which he did that is this. So here's another experiment you can do on your own. Look at something in your room that's like on the opposite side of the room, something that's a little bit further away. Like I'm going to look at a lampshade that I have over there. So look at the thing. Now close one eye while you're looking at it. Put your thumb up over what you're looking at. Go ahead and do it. This will be cool. Now close that eye and open the other eye. Notice how it jumps? That's called parallax. Now, if I know trigonometry, and I do, but if you knew trigonometry, and you may, you can measure the distance between your two eyes and measure the angle of the jump, and that will tell you how far away that object is. The further away it is, the less it jumps. Well, the moon actually jumps a little bit in that kind of measurement if you're looking at it like at the beginning of the night and the end of the night, because we've spent several hours going from one position to another, and it jumps. Well, anything closer than the moon would jump more. Anything further away from the moon would jump less. And Tycho, being such a great observational astronomer, figured out that, in fact, the comets jump less. So he put the comets further out there. That meant these big spheres that were turning all of the planets couldn't be there, otherwise the comet would knock into them. So he was changing the way the universe works. One of the other things that I like about Tycho is that he was an adventurous person. He would fight duels, and one of the things that happened is he was in a fight in college. You always had to wear your sword to class in college. They got into a fight over a prediction that he'd made, and his nose got chopped off. So he wore a fake nose most of the rest of his life. This picture, you can't really tell it's a fake nose, but he had actually multiple fake noses that he would wear. Well, one of the best things about Tycho is that he hired a guy named Kepler. And Kepler took all of Tycho's measurements and all of Tycho's observations. Notice Tycho died in 1601. Kepler spent the next 30 years after that figuring out something crucial. He put the math to the observations. And what he figured out was this. We've been trying for thousands of years to make everything fit a perfect circle. And the truth is, there's no perfect circle out there. Everything goes in an ellipse. And here's the reason why it was a little bit off center or off-putting. We already knew that the Earth needed to be off center. Ptolemy knew that. Well, if you're drawing an ellipse, you take two thumbtacks and some string and a pencil, and you go around. And so the amount here, which we have our semi-major axis, and we have our different points around the two tacks, they stay in relation to each other constant. So our A's here, our semi-major axes, stay the same along the way, and our proportions stay the same. Here's an ellipse. These are all what we call conic sections. Here's a circle. It's also a conic section. A parabola, which is what we typically see from long-term comets, and hyperbolas. They're all part of a three-dimensional cone. We sort of slice a cone. If we slice it straight across, we get a circle. If we slice it at an angle, we get an ellipse. See, an ellipse is just a special kind of circle. A circle is a special kind of ellipse. So a circle is an ellipse where you take those two thumbtacks and put them together, and the distance between them is 0. So they're both, conic sections are both related to each other. So we can call a circle a special kind of an ellipse. We could call an ellipse a special kind of, we could call it an elongated circle. We typically say a circle is a special kind of ellipse. So once Kepler put that idea in there, everything fell into place, and we were no longer getting B pluses and B's and A minuses. We were getting an A where everything fit. Yes, that's where things are in the sky. He also noticed that because we're going around not in a perfect circle, sometimes we're a little closer to the sun, sometimes we're a little bit further away. When we're going on our path closer to the sun, we're going faster. When we're further away, we're going slower. But these areas equal out. That's the second law. And that works out mathematically too. I'm not going to make you do it, so don't worry about it, but just be aware of it. Also, it helped explain why further out planets go slower. Closer in, planets go faster. Mercury whips around in 3 months. We take a whole year. By the time we get out to Pluto, poor Pluto, it may not be a full planet anymore, but in fact, it still follows Kepler's planetary laws. It takes 250 years to go around the sun. It's way, way out there. And those two things are related, how far away it is and how fast it goes, by this simple equation. Again, don't worry about it, not going to make you do it. Then came Galileo. Galileo overlapped with Tycho and with Kepler. He didn't overlap with Copernicus. Copernicus had passed away. But he didn't invent his telescopes until right after Tycho passed away. Kepler got to use Galilean telescopes, but Tycho did not. And one of the things he did was he read about this. There was another guy, oops, not sure what it's doing here, but I don't, okay, let's see. Let me see what's happening here. My Mac is acting up on me for a moment, so I'm going to pause this and we will begin again. Okay, we're going to try this one more time. I don't know why my Macintosh decided to start not letting the program work there, but we're going to try it again here. So let's go back to our PowerPoint and let's scroll down. We were talking about Tycho and Kepler here. So let's go back to Kepler and Tycho, and we were talking about everything going around not in quite perfect circles. And Galileo's telescope, if you have a pair of binoculars 10 by 50 magnification, you can get them for $19.95 at Walmart or Target. You've got a better telescope than one he started with. But he had to build his own and literally grind his own glass. And at first, this was meant to be a military application. You sort of look out over the hills or look out over the ocean and see things coming sooner than you otherwise would have had you seen them only with the naked eye. But Galileo realized you can actually look up and see things through the telescope as well. And one of the things he saw when he looked at the moon was that it had pockmarks. It wasn't a perfect object, and that was a big deal back then. He also looked at Venus. Remember, I told you one of the proofs of Venus going around the sun would be you could see phases, just like we see phases of the moon. Well, he could finally see those. But then here's the real thing. Here's the real thing that said that not everything goes around the Earth. As he was looking at Jupiter, and you can do this with your 10 by 50 binoculars, he noticed that the bright dot of Jupiter spread out into a line of a bunch of different dots. And on different nights, this is actually from his notebook, on different nights, the dots would be in different patterns, but they would repeat patterns. Notice we've got sort of 2 and 1 here, 2 and 1 here, we've got 2 and 1 here, we've got 2 and 1 here, we've got 2 and 1 here. They fit. 3 out of the 4 fit a pattern on a weekly basis, which means as they're moving back and forth, they're moving around Jupiter. How do we know they're moving around Jupiter? Because Jupiter moves through the sky too. And as Jupiter moves through the sky, so do these moving lights. So they have to be going around. And that gave us a confirmation that not everything in the universe goes around the Earth. And so we credit Galileo with one of the key discoveries of modern science. He's also credited with sort of figuring out ideas about gravity. We used to think that heavier things fall faster than lighter things, but the truth is everything falls at the same rate. You can try this experiment at home. Take a piece of paper and a book and drop them. Now, the piece of paper didn't take as long as the book, right? Right. That's not because of gravity. That's because the air was keeping the paper from hitting. Take that same piece of paper, or a piece of paper you don't care that much about, and crumple it up now. Now drop the book, which is probably 200-300 pieces of paper, and the one piece of paper crumpled up. Now drop them. They drop pretty much at the same rate. That's because you're no longer having the air resistance against the crumpled up piece of paper. So pretty much this is setting the stage for a guy named Isaac Newton. And if you have watched the Da Vinci Code, you'll know about Isaac Newton. Up until this point, when people were looking at the sky and trying to figure out where things were, that's all they were doing. They were trying to figure out where things were. They didn't really care how it worked. But from Galileo to Newton, they wanted to figure out how it worked. Why are things doing things the way they're doing? And that's where the laws of motion and gravity come into play. And Newton's laws of motion basically say things tend to stick with what they're doing. That's the law of inertia. If it's just sitting there doing nothing, it's going to sit there and do nothing until something moves it, until something happens to it. If it's going, it's just going to keep going, again, until something outside changes it, until something acts on it along the way. That's why we keep going and going and going around the sun. We're in motion and nothing is stopping us, but nothing's speeding us up either. So inertia isn't just keeping us from moving, it's keeping us from changing whether or not we're moving or not. The second law of motion talks about forces. The more force we can have more mass or more acceleration. You can supercharge like a bullet, you can put a lot of acceleration in it, and that's a lot of force. Or you can have something that's really massive but is moving very slowly, but that's still also going to be a lot of force. If a Zamboni machine runs over you, even if it runs over you slowly, that's a lot of force. A bullet, if it's going really fast, even though that's not a lot of mass, that's still a lot of force if it's fired from a gun. Also, our third law says there's pretty much always an equal and opposite reaction to everything in terms of the forces that are there. So when we are launching a space shuttle or a rocket, for example, the ground is pushing back up as it's pushing down. I'm sitting here in my chair right now. I'm pushing down with about 175 pounds of force, hopefully a little bit less because I'm trying to lose weight. It's pushing up with that same amount. If it were pushing up with more, I'd be catapulted away. If it were pushing up with less, I'd be falling through the chair. So this is an equal and opposite reaction force. And gravity is one of those forces. Gravity is the attraction of any two things to each other. Everything in the universe is attracted to everything else. We often think there's no gravity in space. Well, in fact, there is, but the further away you are from anything, the less you get of that. So it goes off by what we call an inverse square. So here we have two masses. If I have two masses here and I move them twice as far apart, they're 1/4 as attractive. That's what this gobbledygooky equation says. Notice the r squared, and it's in the bottom of our fraction here. That means we're dividing it. And so if you're twice as far away to something, you're only 1/4 as attractive. If you're 3 times as far away, you're only 1/9 as attractive. If you're 4 times as far away, you're 1/16. If you're 10 times as far away, you're 1/100th as attractive. If you're 30 times further away, you're only 1/900th as attractive gravitationally. That also works for light. So Jupiter is further out, it's 5 times further away. It only gets 1/25th the light that we're getting from the sun. It's also only 1/25th as attracted to the sun as we are gravitationally. So I'm not going to make you do things with this equation, but just sort of be aware of that relationship. It's not that there's no gravity, because the moon is 250,000 miles away from us, but it's still attracted to the Earth, and the Earth is attracted to it. On the Earth, we have gravitational attraction, which is pulling us down, and that is an acceleration, and it is 9.8 meters per second, so roughly 10 meters per second. So if you were to throw something off a building like a penny, or you were to jump off a building or something like that, after 1 second, if I had the radar gun, it would look like you're going 10 meters, 10 yards a second. They're close. Close is good in astronomy. After 2 seconds, you'd be going 20 meters per second. After 3 seconds, you'd be going 30 meters per second. So you pick up speed, you're accelerating as you go faster and faster. You can actually watch that with raindrops. If you're sort of watching the raindrops come down and you're out like at the top floor of a tall building and come downstairs to the bottom floor and look out the window, you'll notice the drops of rain, you're seeing them differently because they're accelerating faster when they're closer to the ground. So we are going around the sun. We are going around roughly in 1 year. So we have just a sort of a little bit more than 365 days, which is what we typically call a year. So sometimes we have leap days. We are not going around sort of straight up and down. We're tilted. So sometimes we're tilted towards the sun. Sometimes we're tilted away from the sun as we go around. And we're tilted by 23.5 degrees. So that is our ecliptic tilt. So all of the planets that go around the sun go around pretty much in the same plane. The moon goes around in that too, around the sun, but we're tilted at 23.5 degrees towards that. Because we're tilted sometimes towards the sun and sometimes away from the sun, that gives us seasons. The reason why we have seasons is we are tilted. You can do quick and dirty measurements in the sky just using your sort of pinky and your fist and other kinds of things as you hold it up. I'll let you read this on your own. As you watch things happen through the year, and this is how they built Stonehenge and other monuments like that in the past, when the sun is up in the summertime, it's high in the sky. When it's in the sky in the wintertime, it's lower in the sky. And we can actually follow that pattern over the course of a year. Notice it's sort of lopsided and it has a sort of weird figure 8. That's called the analemma. And the reason why it's a little bit off in one side or the other is because we're not going around in a perfect circle and we're tilted at 23.5 degrees. Wherever you are in the world, your zenith is directly overhead and your horizon spreads out around you. I mentioned this, I believe, in class as well. And everything rises in the east and sets in the west. That is true wherever you are on the planet. This whole area that we look at stars and other things we might call the celestial sphere, even though we know it's not a sphere around us, it sort of looks like that. We have a star at the North Pole called Polaris. There is no southern polar star. So I'll let you look at these concepts on your own as well. Again, that tilt, as we're sort of going around the sun, we're tilted. Well, the sun seems to go, from our perspective on Earth, through different of the constellations. Notice you probably recognize the names of these: Capricorn, Aquarius, Pisces, Aries. These are the zodiac constellations. These constellations are noted for where the sun and the moon go through. People have recognized this for quite some time. Notice we've got this odd one out here, Ophiuchus. That was the 13th zodiac sign, and if you're interested, I'll let you sort of look that up on your own. I may put up a little bit of an extra credit something here sometime so that you can look up a bit about how the zodiac has changed over time. But if we're looking from where we are in Indiana towards the North Star and Polaris, we will see some stars always seem to be around that. The Big Dipper and the Little Dipper are always around that. We call those circumpolar. We can see those every night of the year. Anything that's down on the ecliptic, which is sort of where the sun and the moon go, we're going to lose certain parts of the year because sometimes the sun's going to be in front of them and sometimes the sun's going to be away from them. So we don't see all of our zodiac constellations all year round. But again, remember, season, it's all because of the tilt. Sometimes we're tilted towards the sun. Notice when we in Indiana are tilted towards the sun, Australia is tilted away from the sun. So the opposite seasons will happen on the opposite part of the planet. In the north, when it's summer, it's winter down south. That's why when people were wondering back in March and April, they said, well, when summer comes, the flu goes away. Like, this isn't going to happen. Why? Because the flu goes away in the summer in Australia too. The COVID-19 virus was there in the summer in Australia, so it was going to be here in the summer as well. So that's one of the things that we can note here on our planet is wherever it's winter in one place, it's summer in the other. Where it's fall in one place, it's spring in the other. We always have opposites on the opposite parts of our planet. And that will give us, when the sun is high in the sky for us, it's low in the sky for them. When it's high in the sky for us in the summer, it's going to be low in the sky in Australia. When it's high in the sky in Australia, it's going to be low in the sky for us. Halfway between those two solstice times, the solstice is when it's highest and lowest in the sky, we have equinoxes. And that's where we get basically 12 days or 12 hours of sunlight and 12 hours of night everywhere on the planet. We get a little bit, technically a little bit more than 12 hours of light, because even though the sun dips below the horizon, the glare still keeps us illuminated. So we never actually get on the equinox day precisely 12 hours of night. We've still got a little bit of extra sunlight that's there. Now, as the moon goes around us, it's the one thing that actually does go around us, it wobbles a bit. So we're going around the sun and the moon is going around us. And sometimes the moon will line up and give us eclipses. Sometimes the moon does not line up and it doesn't give us eclipses. There are 8 phases when we go in order where we're sort of growing, we call waxing. So wax on, wax off. Actually, it's not wax off, it's waning. So you start with new moon. What I have here behind me in this image is a new moon, because where I'm sitting, I would be the sun. You can see both the far side of the moon and the Earth. That means if you're standing on the Earth, you're seeing the dark side of the moon. That's the new moon here. Notice half the moon is always illuminated, but from what we're seeing on Earth, we're seeing different quarters or different crescents or gibbouses, or sometimes a full. There are 8 of these phases, and it takes about 30 days to go through the phases. But it actually only takes a little over 27 days for the moon to go around us. The reason why it takes extra days, and we call the difference between this sidereal month, the shorter month, synodic month is the longer month, it's because as the moon is going around us, the Earth is going around the sun, and the phases are dependent upon the sun. So they're keyed to the sun. So there are 2 different ways in which we can measure a month. Lunar eclipses happen regularly because the Earth's shadow is big and the moon goes through the shadows here. That only ever happens at a full moon phase. Solar eclipses are more rare because notice the shadow here from the moon is much smaller and doesn't always actually reach all the way to the Earth. So that can only happen during a new moon phase. So we often get those things in tandem with each other. Sometimes the moon is a little bit closer to us. That's we call the perigee or supermoon. Sometimes it's a little bit further away. That's apogee, or sometimes called the mini moon. If we have a total eclipse of the sun during the apogee, during the mini moon, it doesn't cover the sun completely, and that's called an annular eclipse. Annulus is Latin for a ring. So there's that portion of the lecture. I'm going to let you look at the other PowerPoints on your own, because I don't want to sort of go on for hours and hours and hours about things. But there are some fascinating things that are in those PowerPoints, and I hope that you will take a look at them. It'll talk a little bit about the other planets as well. Let me see, I think there may be one thing I want to share with you in this PowerPoint, maybe 2 things. This picture is one of the more distant pictures of the planet Earth taken from Voyager as it's going out of our solar system. So from a very, very, very far away, we can see the Earth is just a tiny dot, a pale blue dot. Carl Sagan wrote a book called Pale Blue Dot based on that. Our solar system, again, 8 major planets. We have dwarf planets. Is a dwarf planet still a planet? Well, it has the word planet in there. So we have dwarf planets like Pluto and Sedna and ERIS and Makemake and others that are out there as well. Notice Pluto overlaps a little bit with Neptune's orbit. That's one of the reasons why it got demoted there. But I want to show you a couple of things here like this. This shows the planets to scale by size. Notice how small our Earth is compared to the sun and compared to even the larger outer planets along the way. Jupiter is 318 times the size of the Earth, and Saturn is 95 times the size of the Earth. And that's in terms of the stuff that they're made of. But if we hollowed them out and dropped gumballs the size of the Earth inside, we could put more than 1,300 inside Jupiter, and we could put probably about 800 or more inside of Saturn. The rest of this PowerPoint will go through each of the elements of our solar system, the sun in particular. Notice hydrogen and helium gas. That's what it's mostly, and most of our solar system is the sun. And it converts 4 million tons of mass into energy each second. Now that's E equals mc squared. You've probably heard of that equation before. C is the speed of light. That's 300,000 kilometers per second, 186,000 miles per second. So we're doing 186,000 times 186,000 times 400 million. And it's actually even bigger than that because that equation uses the metric system and uses meters rather than kilometers or miles. But what this means is the sun is putting out more energy per second than the entire human race has used in its entire history. So other planets, as we're looking at them, we can tell some key differences. We can tell some interesting changes. So I hope you'll take a look through this PowerPoint and see a little bit more about each of them, including Pluto. These are new images just from the last couple of years. And then we have asteroids. You bet your asteroid we do. And these are important because one of them may crash into us one day. Here's a comet. We actually landed on this comet, Comet Churyumov-Gerasimenko, and no one can say that, so we call it 67P. But we landed on that. We've seen comets hit other planets. Comet Shoemaker-Levy 9 actually hit the planet Jupiter, and those scars on Jupiter are larger than the Earth. So if that had hit us, we would not be in Earth Science class today. Here's the moon. This is the side we see. This is the side we never see, because the side that we see is always facing us. It never turns its back on us. It doesn't trust us. And that's because the Earth has stolen the rotational energy from the moon. The moon is paying us back. It's stealing our rotational energy. The Earth is slowing down because the moon is stealing its energy. The moon is also inching away from us while it does that to balance things out. But these brown and darker gray patches here are called maria. Mare is a Latin word for sea, and they're actually lava fields. And the reason why that's useful information is because we have those here on Earth as well. When we talk about volcanic activity, think about volcanic activity on the moon as well. We have different impact craters on the moon. Those happen on Earth as well. And here, here's the picture I'm using behind us. So we can look at the different planets and see what's up with them. We can see there's some similarities, and we can see there are some differences. So I hope that you will take the opportunity to look at this PowerPoint. This is Olympus Mons. This is the largest volcano in the solar system by size. It may not be the tallest, but it's the largest. This is the size of Missouri. So this is a huge, huge place. You may have seen the movie Total Recall, where Arnold Schwarzenegger is running inside and turning on a machine. Not going to happen. This is like the size of a large state. So this is a huge place here. Notice we have craters. That tells us this is an extinct volcano. It's shut off. If it were still flowing lava, those would have been filled in long before now. And we have this long trench. There was once an idea that there were canals on Mars and little green men, LGMs, that were creating those canals. Maybe that came from this. There was an astronomer named Schiaparelli who wrote about canali, which is an Italian word for channel, not for canal, on Mars. But we do find evidences of water, trickling water, and flowing water once upon a time, dried up riverbeds. And we have these kinds of gullies that seem to still be forming on Mars. And notice the pattern of sort of dampness here on the side. So there's still evidences of ancient water that once upon a time flowed, and different kinds of water, dried up beds. This looks like the shoreline there. So again, I will let you look at these things on your own, and I wish you luck with your quizzes. Remember, all of the information for Chapter 1 quiz should be in the Chapter 1 PowerPoint and lecture, and all of the Astro quiz information should be in this lecture as well as the PowerPoints. And you can use your information as you're doing your quiz. See you in class.